Let's apply the strategy that we described in the previous video to solve ax equals b in the general case. By general case, I mean we'll have some pivot columns, we'll have some free columns. We have to get to rx equals b. So you'll see that this is the general case. The first strategy will always be to start with an augmented matrix. So we'll start with the augmented matrix AB. 1 3 0 2 0 0 1 4 1 3 1 6, and we will augment the vector b 1 6 7. So you've seen before that this doesn't always have a solution, and in trying to find the general solution, we'll check along the way whether we have a solution to begin with at all. Recall the strategy. We are reducing first under the first pivot. The operation is, there's nothing to do in the second row, so we'll just do R3 minus R1 into R3. We apply that on both A and B. So we have 1, 3, 0, 2, 0, 0, 1, 4, then 0, 0, 1, 4. I should have applied those to B as well, but I know that there is nothing happening in the first and second row, so here I just have 7 minus 1, which is a 6. And you can see here that the second and third rows are equal, which is important because if that were not the case, we would not be able to solve the system. So now the next step is to reduce under this 1, which is the second pivot. The operation in question is R3 minus R2 into R3. And what we get is 1, 3, 0, 2, 1, 0, 0, 1, 4, and a 6, and then a row of zeros. Now, note here that this is both U and R. So you could call it U, you could call it R, but I'm going to stick with the notation of R because it has some special properties. And the special properties are that the pivot columns come from the identity matrix. So because there is a 1 and a 0, and they consist of 1s and 0s only, it is very easy to, for example, represent the vector D, in this case, as a linear combination of those two pivot columns. So finding the particular solution is particularly simple when we are working with the reduced row echelon form of A. So we started here with AB. We carried out some elimination. And we got to RD, which in this particular case is the same as UC, but let's stick with RD. Okay, now we described the first step to be to find the null space. So the first step is to describe the null space of A, which is, by the way, the same as the null space of R, which is the solutions to Rx equals 0 or Ax equals 0. But the whole point of going to R is because it's much easier to find the null space of R than it is to find the null space of A or describe. So if you recall, for each free column, we have some non-trivial solution in the null space of R. And even though there are infinitely many, the point is that when you look for those special solutions where you set one variable to 0, one free variable to 0, and or one free variable to 1 and all others to 0, what the key point is that you get linearly independent solutions. To be able to describe the entire space, we actually need linearly independent solutions. Okay, so the columns in green are the pivot columns, the other ones are the free columns. So the variables, I'll write them here. The first column corresponds to x1, the second to x2, the third to x3, the fourth to x4. Remember, when we look at Rx equals 0, we don't look at the column D, corresponds to D, because that's non-zero solutions. So to find the special solutions, the first step would be to set, say, x3 to 1 and x4 to 0. And then we're going to find x2 and x4 by doing, x1 and x3 by doing, okay, I'm sorry, I made a mistake here. This should be x2. So we set things in the free variable. So this should be an x2. Okay, so we need to find x1 and x3. We'll do that doing back substitution. So from here, if you pay attention to the second row, without looking at the 6, so maybe let's focus here. This says x3 plus 4 times x4 must be 0. But x4 is already 0, so really, if this is 0, then, or this multiplies 0, we just have x3 must also be 0. So I'm just going to write that without writing all the equations, but you're free to take some space to write all of these things out. And then when we focus on the first equation, we have x1, that's good, plus x2, 3 times x2. So 3 times x2, x2 being 1, this really is 3 when you replace it in the equation. So we have x1 plus 3. Then x3 is multiplied by 0, x4 is 0, so these two are not important. So we really just have x1 plus 3 equals 0, which means that x1 must be negative 3. So we have one solution. Let's find the other one as well. So from here I could write the first special solution S1 as negative 3, 1, 0, 0. And you can double check that we did this right by taking the dot product of the first row with that vector, and then the second row dotted with S1 is obviously 0 because these non-zeros hit zeros, and then these non-zeros hit 0, so that's obviously 0. And even here, right, that 2 hits a 0, negative 3, 1, 3, 1. When you add them up, you get 0. So this is definitely correct. And then let's set to find the other non-trivial solution. We're going to set x2 to 0 and x4 to 1. And then we're going to do back substitution to find first x3. So focus on the second equation. You see x1 and x2 don't play a role because they're multiplied by zeros. Their coefficients are zeros. So here we have x3 times 1 plus 4 times x4, but x4 is 1, so this really is x3 plus 4 needs to be 0, which means x3 should be a negative 4. And then we have to find x1 from the previous equation. So we focus our attention here. Now x4 is 1, but x3 is 0, so we don't actually look at this at all. And we have x1 plus 2 needs to be 0, which means x1 must be negative 2. And then the solution S2, maybe I'll write S1 and S2 right here. I want to use that other space. So S1 will come here, and S2 is negative 2, 0, negative 4, 1. Obviously, S1 and S2 are not multiples of each other, so they are linearly independent. And if you want to double check your work, just take the dot product of the first row with S2 and take the dot product of the second row with S2 and make sure that those dot products are 0. If they're not, then you've made some calculation mistakes here and you have to go back. So we have S1 and S2, which means that the null space solution in general terms is some constant c1 times the first vector, negative 3, 1, 0, 0, plus c2 times the vector, negative 2, 0, negative 4, 1. So for any choice of c1 and c2, in particular, if you choose c1 to be 1, c2 to be 0, you get s1. If you choose c1, 0, c2 to be 1, you get s2. And then if you choose c1 and c2 to be anything but those 1 and 0 combinations, you get new solutions to ax equals 0, but they're in the space described by these two special by the special solutions. All right, now let's describe a particular solution. So a particular solution literally says you want x1 times the first column, 1, 0, 0, plus x2 times the second column, 3, 0, 0, plus x3 times 0, 1, 0, plus x4 times 2, 4, 0, and I need a bit more space. Equals 1, 6, 0. Remember, we just need one combination of the column vectors. There is more than one. Because there is a null space, we know that there is more than one solution, but we just want one. And the easiest one is the one that will only use the pivot columns. What we mean by that is that I will set x2 to be a 0 and x4 to be a 0 in my combination. And then I will set x1 and x3 to be what they need. Well, x1 has a non-zero only here. So when you combine that 1 and that 0 to get a 1, you know x1 must be 1. And then no matter what x1 is, you get this 6 only from x3. So it's very clear that x1 must be 1 and x3 must be 6. And the respective coefficients components of B will always tell us what x1 and the corresponding x's in the pivot columns must be just from these entries. So it's immediately clear that x1 must be 1 and that x3 must be a 6. So the particular solution xp is 1, 0, 6, 0. So we have found the particular and we have found the null space solution. Then the general solution, I don't want to switch boards, so I'll just write it up here. Is x equal to c1 negative 3, 1, 0, 0 plus c2 times negative 2, 0, negative 4, 1 plus 1, 0, 6, 0, where the numbers c1 and c2, where c1 and c2 are some real numbers. So you see the general solution describes infinitely many solutions, but they have a vector space structure coming from this linear combination over here, shifted by that particular solution 1, 0, 6, 0, choosing literally any numbers c1 and c2 and replacing in here, computing that combination will give us a solution to ax equals b, and you could just test it out. Add some values here, get some new vector x, carry out the multiplication a times x, and verify that you get